This is from our friend Bjorn, who is a research fellow at Monash University after having received his PhD in bioinformatics at Bielefeld University in Germany. And I believe Bjorn and his students won an award for their stereoscopic presentation work here just a few years ago. So we look forward to seeing what they're doing this year.
Yeah, so Greg, thanks a lot for the kind introduction. Yeah, I'm very excited to be at this very nice conference again. I was the first time here in 2014. I will also have a few references included in the talk today. In the talk I will give today, there were a number of co-authors included. First of all, thanks a lot to their contributions. When the paper is published later, please have a look to the paper if you're interested in this topic. So first of all, I would like to give a short introduction to Immersive Analytics, our initiative for Monash University. Actually, it's led by these three very nice guys, Professor Kim Marriott, Falk Schreiber, and Tim Dwyer. And as you can see there, there's a hint hidden in this slide. So at the moment, I'm still at Monash University, but in a few weeks, I will join Falk Schreiber to Konstanz University, so I will move back to Germany. And of course, we are planning to have a very close collaboration on this topic, and I think it will be quite excited to work also over this large distance together on this topic. So here, just a few examples what we are doing. This talk actually will be about cave navigation. So I personally am working with visualization of cells, and especially in context of using this nice Cave 2 environment. I'm doing large-scale visualization of cells. This is just an example there. And one of my colleagues, Maxime Corday, he's working with HMDs. And as you know, HMD is also a very important topic at this conference. And he's using these HMDs to analyze trajectory data and using new interaction techniques by combining the leap motion with the Oculus Rift. But I think also at this conference there are some examples about this. But why am I saying this? So I think I don't have to be a prophet to say that 2016 is the year of HMDs. And I think also that many application areas which were normally taken into account by using caves will now be redirected and will be used in context of HMD visualizations. So, of course, still many application areas are reserved for caves, but I think what we have to do now for the application areas which are used in context of cave, we have to optimize them. So, and one of these application areas are group presentations. So here you see an example, and I come now to a basic problem which we argue in the paper. With cave presentations, you have the presenter in the cave, so the navigator, and you have the group. So in our cave in Monash University, the Cave 2, which is originally invented also in USA, you have something like 10 to 20 people, and you have here the navigator. So if we are looking now at the navigation, we can see here, first of all, the visualization is optimized for the navigator, which means we are using head tracking, especially in terms of stereoscopic visualization, to optimize the eye distance and to optimize the projection matrix. And in addition, also, the perspective is changed. So if the navigator or the presenter is moving inside the cell and inside this virtual environment, then also the perspective is changing. This is very nice, no question, for the presenter. This is perfect. But what about the audience? Because the audience is at their fixed position, and it's not really the way what is expected by the audience. This is one thing. The other thing is also the navigation. So we have a first-person-like movement. So normally we are using a wand for the navigation. And also the wand is a very nice approach for the navigator, but also for the audience is quite unexpected because you have a first-person-like movement, but you are fixed as the audience. So these are two examples which we are taking into account. At this talk, I will focus at the stereoscopic visualization. Originally, we wanted to include it both inside this paper, but we decided then to make two papers out of that because it would be too much content. So let's come to the methods. We call our method the space map. So on one hand, the navigation, which I only will shortly say a few words about this. The basic idea is that you have a 3D representation of your environment. So you see an overview map of your 3D environment, and you can use this map to navigate inside this environment. You will see later on a video about this. So you have, for example, different tour points, and these tour points you can select in 3D space. You can also select them in 2D space. But for this talk, more important is, of course, the stereoscopic visualization. So what we were using is the approach from 2014, because we used the software, which I will show on the next slide, which is used to optimize the stereoscopic effect. And this effect we apply now also to the 3D environment of our cave. So this here is now our Cave 2 plus zSpace approach. I think some of you who have been here already in 2014 saw the first version of the zSpace. It's the zSpace 100. And we are actually using the zSpace model 200. So, what you are seeing here is, on one hand, you have the large cave in the background, and you see here the composition of the cave, or the working area. So you have here 20 different node computers, and each of these nodes is connected to 4 different monitors. So, and each of these nodes is connected to a server. And this is a normal Cave 2 configuration. And here you have now also the communication between the zSpace system, which you see actually here, and the server, which is, again, communicating with the nodes. You see here it's not completely 360 degrees, it's 330 degrees, so here this is the entrance. Here, in addition, you see also a 2D monitor attached to the system. This was especially used for our evaluation, which I will talk about on the next slides. So this is the software which we are using, and it's the same software we presented here in 2014, but it's now more advanced. So in 2014, we just discussed how to optimize the stereoscopic effect. And in addition, we use this software also. You see here a new paper. It was presented at last year at the BDVA conference in Hobart, at an IEEE conference. And there we just use the zSpace for using new navigation techniques. And if you're interested in this, please come to the demonstration session tomorrow, because I have the zSpace with me too. I could not take the cave with me, sorry, but it was, of course, I can show you then the approach by using our zSpace system. So you see here that you have these different tour points, and also here you see the 2D representation of these tour points, which is, of course, here a more traditional representation. And here you see also just a list. All this we used for the evaluation. And here you can also see how you could optimize the stereoscopic effect. So now on the next slide, you actually see the approach of our stereoscopic adjustment. So first of all, we have here default value. So this you can just optimize for your eyes, the eye distance. So, and this here are actually graphics published in 2014. So we have here a specific formula, and this formula we are using to change the eye distance. Why do we need to change the eye distance? In a normal 3D environment, through a normal virtual world, you normally don't have to optimize the eye distance. But we are doing cell visualization, and the problem in cell visualization is, this here, for example, represents a cell membrane. The cell membrane is something like 9,000 nanometers. And if you go down to the molecular level, then you have something like 0.1 nanometer. So you have this distance in scale, sometimes of 100,000, sometimes of the factor of 10,000, and this has to be optimized. So what we are doing is, we have here just a pick ray. We always get the closest position to the nearest object, and then we use, by computing this formula here, we change the eye distance. So it's, of course, a quite simple approach, but quite effective. So, and this approach we actually apply now also to the cave. This means we pre-compute the stereoscopic eye distance in our space map, and then we apply it to the cave. So, and now we come to the experiments, which is important for these experiments. We wanted to have, this is an expert review, so we only wanted to have people who had already a lot of experience with the cave. So we have actually, you will see it on the next slides, 8 participants. And it was a quite demanding review because each of them were working something like 1 hour on the cave. And you see here that we have 2 major scenarios, each subdivided into 3 sub-scenarios. So first of all, our new approach, we use the zSpace in combination with the Cave 2 system. Then we had the linear tour with the zSpace, which was actually just consecutively go through the different tour points. Then we had here the tour points in 3D space, where you had to select 3D points, and then automatically the view was changing to the specific points. And then we had the free navigation, where you could freely navigate through the space map, choose a specific perspective, and then project it onto the cave. So, and then we had here the cave-only scenarios. So these are the classical scenarios. Again, it's quite similar, and here you see what was important. We also had the navigation with the wand to compare it to our approach. But now for our stereoscopic visualization, at each of the scenarios, 5 times, the participants have to manually change the stereoscopic effect. So this means they just had a slider, like you know it maybe from tools like VMD or Amira. These are tools which are used in the bioinformatics community, for example. And then we used our automatic stereoscopic eye distance adjustment approach. So, and now we come to our example. You need the glasses again. So this is actually now the tour points in 3D by using the zSpace. Yeah, so here you see sitting in the cave with the zSpace, and you see here actually the space map. So you can freely navigate through the space map. You can select now different points, and you can now see this is a stereoscopic screen. Here you have also the stereoscopic visualization, and now you can use the head movement to change the view in this environment. This you can actually try also tomorrow when we give our demo session here. The different arrows represent the camera positions. This is the distance of 30,000 nanometer, 10,000 nanometer. Then the next one will be 1,000 nanometer. So this is always the distance between the eyes and the distance between the objects in 3D space. And here 100 nanometers, and finally we have 10 nanometers. Yeah, let's come to the results. So as I said, we had 8 participants. This is now the warming up question. So we just wanted to know, so you will not need the glasses anymore. You can take them away. So first of all, we wanted to know how is the attitude towards stereoscopy. And of course, it was positive because they were working every day with stereoscopy. If we would have something like 5 students, I think we would have a quite diverse view to nowadays. So, but now let's come to the more important part. So here we had now different questions, which were asking how did you like the quality of the different approaches. So first of all, this line here, the blue line, represents the autostereoscopic quality of the zSpace. So this was already quite good, and we were developing at this already a longer time, so it's not a big surprise that this got quite good results. Then also for the cave, if you're looking at this line here, then you also see this was already quite good results. So then the combined autostereoscopic effect, you see here already it's okay. It has quite a fair result, so it's still okay, but it could be improved. 2 said it's good, and 6 of the participants said it was fair. So there's still some room for improvements in this. Then you see here, very important, the parallel usage of the stereoscopic effect. Most of them said it was very nice, but we had here one outlier, and this was actually what you always experience if you do stereoscopic experiments. So as I said, it was quite demanding. You had to change the stereoscopic effect about 1 hour. And this person here got really headaches from that because he always had to change the view. He tried to reach an optimal configuration, and this was quite demanding. So in this case, for this guy, it was really too much. So also the refocusing, this was an interesting question because we wanted to find out if I have to change the focus point, is it a problem to change between 2 stereoscopic devices? And obviously there was more or less no problem. Here 2 said, okay, a little bit. And again, we have here our outlier who said, okay, it was just too hard for me. Now finally, we come to a question according to different VR focusing aspects. So we were asking, was the automatic effect optimal for you? Was the manual one optimal? Or do you say both were fine? And so first of all, you see, this is no surprise. In terms of speed, of course, the automatic effect wins. And also in terms of attention. This means if you have to change it manually, of course you have to focus on the space map or whatever you are using at the moment. It's a slider, and you don't notice what is going on in your environment. So this was the first very positive examples. Then also very important here, the overall rating is quite good for our approach. So nobody said, okay, I preferred the manual one. Then in terms of orientation, also the space map was winning. But then we come to the immersion. Immersion was not so good in this environment. I think, yeah, because you had always to change between the 2 different views. And of course, as you know, we were using 2 semi-immersive displays. So you don't have the full immersion with that. And then finally here, important, the precisions you see, there's only a very small advantage for the manual adjustment, and the automatic one is still quite nice. Yeah, we come already to the final slide. So we see in overall, looking to the conclusions, that basically the green is just symbolizing that we had a lot of positive feedback. Here the yellow one was, for example, fair. So this means in combination, there's still room for improvement. But of course, as I said, we did a lot of experiments over a longer time. So this was very demanding. You always had to switch between manual and automatic movement. If you optimize it only for one presentation, then it should be very nice. Yeah, so we just discussed about this, especially in terms of overall rating, attention, and speed. We had good results. Orientation and immersion was still okay. But here you see in terms of precision, of course, still the manual one is a little bit better. Yeah, with this I come to the acknowledgements. First of all, thanks a lot to the participants and my co-authors. Then thanks to a number of open source tools. Lightworks is working on open source. They are not completely open source by now. And of course, thanks for your attention.